All right, here are a couple example problems that emphasize an important concept. Physical properties or physical changes are determined by the intermolecular forces. So if you have really strong intermolecular forces that make certain physical changes like boiling or melting much more difficult to do. So you're going to have a higher melting point or boiling point if you have strong intermolecular forces, because melting and boiling is breaking those intermolecular forces so that the molecules can separate themselves and become more distant from one another. Likewise, you could say that the chemical properties, like reactivity, depend on the strength of their intramolecular forces or their bonds. So if you have a very strong bond, it's not going to be very reactive. And if you have a very weak bond, it will be more reactive. That's the general concept we want to talk about here. Intermolecular forces have an impact on physical properties, and intramolecular forces or bonds have an impact on, or the strength of those bonds have an impact on their chemical properties. So let's do a couple examples. Observe the data table above to explain the molecular interaction and its strength for water and ethanol. Okay, so water has a higher boiling point than ethanol and a lower vapor pressure than ethanol. Remember that vapor pressure is the pressure exerted by the vapor molecules within the substance at a given point. So if it's exerting less of a vapor pressure, that means those bonds are not being, those intermolecular forces are not being broken. It's not trying to spread out and form a different state of matter or to change into a gas. So we could say, again, boiling point of water is greater than the boiling point of ethanol. And we could say that the vaporization pressure, let's just call it VP, of water is less than the vaporization pressure of ethanol. Both of these facts point to the same thing. And what they tell us is that the intermolecular forces between water molecules are stronger than the forces between ethanol molecules. So something that we can keep in mind. The intermolecular forces must be stronger in order for the boiling point to be higher. All right, let's go on to the next one. In combustion, so now we're talking about a chemical change. In combustion, oxygen gas reacts with the compound combusted, but nitrogen gas doesn't explain this phenomenon. So what that tells us is that oxygen's reactivity is greater than nitrogen's reactivity. Or you could say oxygen is more reactive than nitrogen is. So what that tells us is the covalent bond in O2 is weaker than the covalent bond in N2. So the bond in O2 is weaker than the bond in the N2 molecule. And why is that? Well, we could actually draw the structures out. Oxygen has 6 valence electrons multiplied by 2 because oxygen is O2. So we have 12 valence electrons. You draw oxygen, That's 2, 4, 6, 8, 10, and then 12. Obviously, this oxygen's not happy, so I would need to erase this bond and make it a double bond. So we have double bond in oxygen. But if I go and draw nitrogen, nitrogen has 5 valence electrons multiplied by 2. That gives us 10 valence electrons. So let's draw that out. Nitrogen, 2, 4, 6, 8, and then 10. You can see that neither of these nitrogens is happy, so I've got to erase one pair of electrons and try making a double bond. Well, now I've got 2, 4, 6, 8. This one's okay, but the one on the left is just 2, 4, 6, so it's not happy yet, so I've still got to erase a couple more electrons and make another bond, so we end up with a triple bond. This one has a triple bond. And if you remember, triple bonds are stronger than double bonds. So that would explain why the covalent bond in O2 is weaker than the bond in N2. A triple bond is stronger than a double bond.